Conservation of energy. The first thing that we have to do is figure out what our system needs to be in order for energy to be conserved. So we're going to talk about systems first. If you have ever observed energy in action around you, you may have noticed that energy doesn't always seem to be conserved. The kinetic energy of a soccer ball is soon gone, right? It comes to a stop. Even on smooth ice, a hockey puck eventually stops moving. The swings of a pendulum will soon die away. So that seems to break the law of conservation of energy. Where did that energy go, since our law states that energy is always conserved? So another way to think about that is to think about money. If you had $100 of cash in the bank, one day you counted your money, and despite neither earning nor spending anything, you were 50 cents short. Would you assume that the money just disappeared? Probably not. More likely you'd go hunting through your purse or pants pockets, trying to locate the lost change. If you couldn't find it there, you might look under the couch cushions or even in the dryer. In other words, rather than giving up on the conservation of money, you would seek new and different places where it might be. Scientists have done the same with the conservation of energy. Rather than concluding that energy is not conserved, they have discovered new forms into which energy can be converted. They have concluded that the law of conservation of energy is a description of nature. That is, as long as the system under investigation is closed so that objects do not move in or out, and as long as the system is isolated from external forces, then energy can only change form. The total amount of energy is constant. In other words, energy cannot be created nor destroyed, which is kind of how we have described the law of conservation of energy for a while. So here are key words, though, that have to be used in order for the law to hold true. Our system must be closed, nothing leaves or enters, and it has to be isolated, which means only internal forces. So, mechanical energy first. Mechanical energy is the sum of kinetic and potential energy, which is the two types of energy that we learned about last time. The UG, remember, is gravitational potential energy. So the sum of gravitational potential energy plus kinetic energy is equal to mechanical energy. So imagine a system consisting of a ball and earth. Suppose the ball has a weight of 10 newtons and will be released 2 meters above ground, which you define to be the reference level. Because the ball isn't yet moving, it has no kinetic energy. Its potential energy is represented by 10 times 2, which is 20 joules. The ball's total mechanical energy is therefore 20 joules. As the ball falls, it loses potential because it's getting closer to Earth, and gains kinetic because it is speeding up. When it is 1 meter above Earth's surface, its potential energy is 10 joules. What is the ball's kinetic energy when it is at a height of 1 meter above the Earth? The system, which consists of the ball and Earth, is closed and with no external forces upon it, is also isolated. Thus, its total energy remains constant at 20, which is what we started with. So 20 minus 10 equals 10. When the ball reaches the ground, its potential energy is 0, and its kinetic energy is now the full 20 joules. The equation that describes conservation of mechanical energy is the energy before equals the energy after, which may be rewritten like that. if you prefer. What happens if the ball doesn't fall down but rolls down a ramp? Without friction, there are still no net external forces, so the system is still closed and isolated. The ball still moves down a vertical distance of 2 meters, so its loss of potential energy is still 20 joules. Therefore, it still gains 20 joules of kinetic energy. The path it takes doesn't matter. So it doesn't matter if we roll down a ramp or a hill or if we fall, it's still going to be the same amount of energy transfer. In the case of a roller coaster that's nearly at rest at the top of the first hill, the total mechanical energy in the system is the roller coaster's gravitational potential energy at this point. Suppose some other hill along the track were higher than the first one. The roller coaster could not climb such a hill because doing so would require more mechanical energy than is in the system. So if you were ever to design a roller coaster, you would want to make sure that this held true. The first hill must be the highest hill. If we think about a pendulum that is oscillating, the system of the pendulum would be the bob plus the earth. Usually, the reference level is chosen to be the equilibrium position of the bob, which would be the position of it hanging straight down. Work is done by an external force in pulling the bob to one side. This gives the system mechanical energy. At the instant the bob is released, all the energy is potential, but as it swings down, the energy is converted to kinetic, because again, it's speeding up as it swings down. When it swings out to the side, it has to stop for an instant and turn around and swing back the other way. So therefore, at those two positions, its kinetic energy is 0 and its potential energy is at its maximum amount. So the loss of mechanical energy, what happens there? So we have an oscillating pendulum, which eventually dies down. A bouncing ball comes to a rest. The height of a roller coaster gets lower and lower as you progress through the roller coaster. Where does the mechanical energy in such systems go? Any object moving through the air experiences the force of air resistance. In a roller coaster, there are frictional forces in the wheels. When a ball bounces, the elastic potential energy stored in the deformed ball is not all converted into kinetic energy after the ball bounces. In each of these cases, some of the original mechanical energy is converted into thermal energy within the members of the system. As a result of the increased thermal energy, the temperature of the objects in the system will rise slightly. Albert Einstein recognized yet another form of potential energy, mass itself. He said that mass, by its very nature, is energy. The energy, which he used E0, is called rest energy, and it's represented by his famous formula, E equals mc squared. According to this equation, stretching a spring or bending a vaulting pole more causes the spring or the pole to gain mass. Likewise, a hot potato weighs more than a cold one. In these cases, the change in mass is too small to be detected. When forces within the nucleus of an atom are involved, however, the energy is released into other forms, such as kinetic energy. Changes in mass can be relatively large. All right, so there are 3 problems that you're going to do on your own. 1, 2, 3. Here is an example problem just in case you need a little help getting started. So our primary equations that we're going to use are these right here: kinetic and gravitational potential energy. So a large chunk of ice with a mass of 15 kilograms falls from a roof 8 meters high. Ignoring air resistance, find the kinetic energy of the ice when it reaches the ground. So we are not given the velocity at all, but if I know the potential energy at the beginning, so at the top, maybe that would be better. Potential energy at the top, that's going to be equal to the kinetic energy at the bottom, right before it hits the ground. So I'm going to use what is given in the problem to first calculate the potential energy. G, of course, is 9.8. Our question asked for the kinetic energy. Okay. So 15 times 9.8 times 8. So we're going to start with 1,176 joules of energy. And that, although I use the potential energy equation, that amount of energy is equivalent to its kinetic energy. So that is my answer to letter A. What is the speed of the ice when it reaches the ground? So now that I know the amount of energy that it starts with, I can use the kinetic energy equation to solve for velocity. I know mass. Mass is 15. Plug that in there. Okay, I'm going to solve for V. And it's V squared, which means I need to take the square root to isolate V. The ice chunk is going 12.5 meters per second before it reached the ground. So, 3 problems for you to do on your own. Let me know if you have any questions.